section 10.2. We're doing more of the same. Systems of equations. We're going to convert them to matrices, and we're going to solve them. But I don't know if you noticed, when you did your homework last night, every time there was only one solution. You notice that? There's exactly one solution. So, do you remember when we talked in the past what an equation looks like that has three variables? Say ax plus by plus cz is equal to another number. If I graph this on the x, y, z axis, what does that equation look like? I didn't mention it. It was weeks ago. Section 9.2. It's a plane. Yeah. It's a plane in 3 dimensions. So if I have 3 planes, what are all the different ways that they can intersect? A lot of different ways, right? We just looked at the ways where they intersected at one point. That was 10.1. You looked at only this scenario, but there's all these other scenarios we ignored. Let's go back here. 10.2. Okay, on 2 variables, our equations were lines. And we would have either single solution, no solution, because they have no points in common, or we said they're the same line, so there's infinite solutions. We call that a dependent system. When it's a 3-variable system, section 10.1, we always had one solution. That makes all 3 equations true. In this scenario, do you think this is an inconsistent system or a dependent system? So dependent means infinitely many solutions. Inconsistent means all 3 are not true simultaneously. So for instance, this point here is on the dark blue plane and this light blue plane, right? But this point is not on this last plane here. Does that make sense? So can you tell that there is no point that is on all 3 planes? Always one is missing. So this is what we call an inconsistent system. If they're parallel, there's no point that's on all 3 planes. If 2 planes are the same and the third one is not, it's parallel to it, it's also inconsistent. So maybe I should write that these 3 are inconsistent. I'm not going to ask you to graph these. So instead, what you're going to do is combine them using the matrix operations, and you're going to get something at the end like 3 equals 7 or 0 equals, and you'll conclude it's an inconsistent system. All right, this other scenario, we'll say these other 3. We have 3 planes that intersect all along the same line, so there's infinitely many solutions along this line. If these 2 planes are exactly the same, this one is not, still has a line, and there's infinite solutions here. And if all 3 planes are exactly the same, then we have infinite solutions along this plane. Okay, in all of these scenarios, they're dependent systems with infinite solutions. And today, what will be different from when you did this in the past with elimination method, we now need to write what those infinite solutions are explicitly. The good news is it tends to be less work when the problems are inconsistent or dependent, but it takes more interpretation at the end. What's the first step here if I want to solve this? In chapter 10, we ignore all the variables and the equal sign, and we just write the numbers. Coefficients of x are 1, 4, 7, -3, -1, 1, 2, 3, 4. Did anyone ever copy these numbers wrong? And then hate yourself for having to do the problem all over again? Okay, it's just me. What's this matrix called? What's a vocab word from yesterday? Yeah, it's an augmented matrix. What's the goal? Let's do Gauss-Jordan elimination. Yeah, so we want to work with the first column. In this first column, I want this to be a 1. It is. And I want to make these a 0. Oops. I want to make this a 0. I want to make this a 0. So let's do -4 times row 1 plus row 2. We'll keep row 1 the same. 1, -3, 2, 6. Now we'll apply this operation. So -4 times row 1. Did you find a systematic way to not make errors? -4 times row 1, -4 times 1, -4 times -3, -4 times 2, -4 times 6. And we add them to the second row. -4 plus 4 is 0 like we wanted. That was the whole point of it. 12 plus -1 is 11. -8 plus 3, -5. And -24 plus 10 is -14. All right, how would we make, we must use row 3 this time. And how would we make that 7 into a 0? -7 times row 1 plus row 3. Okay, I'm going to write -7 times row 1 on the bottom. -7 times 1. -7 times -3 is +21. -7 times 2, -14. And -7 times 6 is where I struggle. Is that -42? And we add these. 7 plus -7 is 0, as we wanted. 21 plus 1 is 22. 4 plus -14, -10. -2 plus -42 is -44. All right, any thoughts on the next step? I want this to be a 1. I want this to be a 0. And I want this to be a 0. That's our next goal. Let's make this a 0 using the 11 because it looks like I could just do -2 times row 2 plus row 3. Okay, so -2 times 0 is 0. -2 times 11 is -22. It's really hard to see. -22. -2 times -5 is 10. -2 times -14 is 28. So if we add these together, we get 0 plus 0 is 0. -22 plus 22 is 0. 10 plus -10 is 0. And what's 28 plus -44? The -16? Okay, I'm going to keep row 1, row 2 the same because this already tells me the answer. Can anyone tell me what the answer is? Inconsistent. Why is this inconsistent? Very good. So this equation here means 0x plus 0y plus 0z is equal to -16, which is absurd. That's never true for any value x, y, or z. So we say it's an inconsistent system. And there's no solution. Any questions about that? Honestly, that's what I'm rooting for on these problems. That's the least amount of work, easy to interpret. Let's try this one. What would this be as an augmented matrix? Maybe we subtract x from both sides. And as an augmented matrix, we get 0.25, -0.75, 1, -1, 3, -4. What's the first step? Bless you. Okay, so you want to move this one up here, but make it positive. So negative row 2, that would be 1, -3, 4. You want to get rid of the decimals? How would you get rid of the decimals? Times 100? 100 row 1 is 25, -75, 100. All right, now what? Want this to be a 0. -25 R1 plus row 2. So that would be negative 25, 75, negative 100. 0, 0, 0. Row 1 will keep the same. 1, negative 3, 4. So what does that mean? This equation is 0 equals 0. And this equation is x minus 3y is equal to 4. So this is a dependent system. What we found out was both equations were exactly the same. So we have infinitely many solutions. It's a dependent system, but we need to list all those solutions. We call this the dependent variable. The column with the 1 in it contains the dependent variable, and we like to solve for that dependent variable. You solve for it, you get x is equal to 3y plus 4, and we call this y the free variable, meaning y can be whatever it wants, it's free. But whatever it picks, x is then dependent on it. When we write the solution set, we say, let y can be any real number. And whatever we pick for y, then x must follow a distinct pattern. That is, x must be 3y plus 4. Are there any questions about this notation? What this means is the solution set in curly braces. The curly braces means the solution set is all ordered pairs of the form 3y plus 4 comma y. This red vertical line means such that y is any real number. So this is shorthand for this sentence. Given that, can anyone tell me what one solution is? There's infinite. Can you give me one? Okay, so y can be anything. So pick your favorite number. 2. And then what must x be? 3 times 2 plus 4. 10. Can anyone give me a more simple solution? Pick y is 0, and you get x's. Okay, so pick it, plug in whatever you want for y. Any questions about that? And your homework does ask you to list 3 solutions. There is more than one way to write this. I could have solved for y instead of x. So if I solve for y instead of x, I would have negative 3y is equal to negative x plus 4. Divide by negative 3 to get y is equal to negative x plus 4 over negative 3. We can write as x minus 4 over positive 3. And so I could equivalently write my solution set where x is the free variable and y depends on x, meaning y is the form of x minus 4 over 3, such that x is any real number. So these are the exact same solution set, but there's more than one way to write it. So either of these answers is acceptable. Any questions about this? All right, let's solve this problem from example 3. As an augmented matrix, my coefficients of x are 1, negative 2, 1. My coefficients of y are negative 4, 9, negative 7. And my coefficients of z are 7, negative 16, 13, and constants 14, negative 31, 23. You want to practice this one on your own? Why don't you practice this? See if you can come up with an efficient way. Are these the row operations you decide on? And it doesn't have to be. Many ways to do it. All right, so I'm going to continue solving. These are probably the most efficient row operations we could pick, but not the only ones you have to do. So 2 times row 1 plus row 2 would make this into 0. And then row 1 minus row 3 is a way to make this one into 0 also. Okay, from there, we'd really like to make this a 1 which it is, and then use that to make the one above it into a 0 and the one below it into 0. So I'm going to, on the top, do 4 times row 2 plus row 1. So 4 times row 2, 4 times 0 is 0. 4 times 1 is 4. 4 times -2, -8. And 4 times -3 is -12. So if I add those, I get 0 plus 1 is 1. 4 plus -4 is 0. -8 plus 7 is -1. -12 plus 14 is 2. I'm going to keep row 2 the same. 0, 1, -2, -3. And then to make 0 on the bottom, I'm going to do -3 row 2 plus row 3. So -3 times row 2. So -3 times 0 is 0. -3 times 1 is -3. -3 times -2 is +6. And -3 times -3 is +9. So when I add these together, they all cancel, and I get 0, 0, 0, 0. So now there's no way for me to eliminate these numbers, -1 and -2, because I only have 0 to work with. So I can't get rid of it. This means that the bottom equation is 0 equals 0. As long as we don't get anything inconsistent above it, it's a dependent system. So the top equation corresponds to x minus z is equal to 2. And the bottom one is y minus 2z is equal to -3. So in this case, we say that x and y are the dependent variables, and they depend on z, which we call the free variable. So we'd like to solve for x. X is equal to z plus 2, and y is equal to 2z minus 3. So we have infinitely many solutions for a dependent system, and we want to write down what they are. So they're ordered triples of the form z can be anything. And once z has been picked, x has to be z plus 2, y has to be 2z minus 3. So all ordered triples in 3D space of this form, such that z is any real number. How we're going to write our solution set. Any questions about this? So there's infinitely many solutions. Can anyone give me one of the solutions? Good. If z is 0, we can pick anything. Then we get -3 for y and 2 for x. I think your homework asks you to list 3 solutions. What's another solution? Maybe 1 for z. Then we get 3 for x. -1 for y. I don't know. Z is equal to 2 or -1. So let's write -1 for z. And we get -5 for y and 1 for x. If you're feeling really crazy, plug in like e or pi. The point is you can plug in anything, any real number. All right, let's do this problem. 1, -1, 2. 2, -2, 4. 3, -3, 6. And 6, -6, 12. We want this top number to be a 1 and use that to make these bottom ones zeros. Let's do row 1 plus row 2. And on the bottom, oh, let's do that first. So row 1 stays the same. 1, 2, 3, 6. And if we add row 1 and row 2 together, we get 0, 0, 0, 0. Okay, that's easy. What should we do on the bottom? We must include row 3, right? Yeah, -2r1 plus r3. Or we can do to R2 plus R3. In either case, what do we get? 0, 0, 0, 0. Okay, so this is a little different than the last problem, but that makes life easy. 0 equals 0, or x plus 2y plus 2z, no, 3z, thank you, is equal to 6. What's our dependent variable? X dependent variable. What's our free variable? We have two free variables. Y and z can be anything. So we want to solve for x. X is equal to negative 2y minus 3z is equal to, plus 6. So we subtract 2y from both sides, subtract 3z from both sides, and our order triples are of the form z can be anything, y can be anything. Once those free numbers have been picked, then we say x must be of the form negative 2y minus 3z plus 6. So all order triples of this form such that y and z are any real numbers. If you're feeling a little lazy and you want to write cool math notation, it can be abbreviated a little bit further into y, z in the set of real numbers. All right, any questions about this? We must get this side into Gauss-Jordan form. So if I stop and this equation's all zeros, the middle equation might be inconsistent. 1 equals 2, or sorry, 0 equals 2, right? So the answer is no. You stop when you get the left side in the Gauss-Jordan form, and we can interpret that. But yeah, it's a good question. When you stop, when do you know you're done? But for inconsistent system, if you get 0 equals 2 at any point, you know you're done. So that's a little different from a dependent system. Any other questions? Can you give me one solution? 6, 0, 0. Good. Yeah, pick y equals 0. It's a free variable. Pick z is equal to 0. And then x is determined. What's another solution? What about y is 0, z is 1? Then what's x? 3? Wait. Yeah, that's 3. And then what if y is 1 and z is 0? We get 4. Example of 3 of many solutions. So in case you're curious, what we're saying in this case is all 3 planes are the same. So all these solutions are all on the same plane. Whereas the previous problem, they all 3 intersected in a line. So all these ordered pairs were on the ordered triples are on the same line. But you don't need to know that. It's just the dimensions depends on how many free variables. So if we have one free variable, z only, then it's a line. If we have 2 free variables, like y and z, then we're really saying they're all on the same plane. There is time to do this. Yeah, let's go ahead and do this problem. Find an equation of a plane that passes through the points 1, 2, negative 3, negative 2, 0, negative 7, and 0, 1, negative 4. Okay, so the key piece of information here is the equation of a plane can be written in the form of ax plus by plus c is equal to z. Okay, so first we use the ordered triple 1, 2, negative 3, and we plug in, what if x is 1? Then I get a. What if y is 2? Then I get 2b. There's nothing to plug in there next to c. And then we're saying z is equal to negative 3. Are there any questions about that? So I plugged 1, 2, 3 in for x, y, z. Next, we do the same thing for -2, 0, -7. So what would that equation be? Plus c is equal to -7. Very good. And we do that with the third point, 0, 1, -4, to get b plus c is equal to -4. So we have a system of three equations with three unknowns. It's possible that we have a single solution. If we find a, b, and c, then we know the equation we're playing. So as an augmented matrix, I have 1, 2, 1, -3 is my first equation. -2, 0, 1, -7, 0, 1, 1, -4. We want to make this into a 1. It is. Make this into 0. It is. That's nice. So the next step, make this into 0. Let's do 2 row 1 plus row 2. Actually, I want to put that on the bottom line. 2 row 1 plus row 2 on the bottom line. Okay, so that would give me, let me write 2, 4, 2, -6, and add it. 2 plus -2 is 0. 4 plus 0. 2 plus 1 is 3, and -6 plus -7 is -13. I'll keep row 1 the same. Let's make it 1, 2, 1, -3. And I must include row 3 also in some form. And row 3 is how I want it already. 0, 1, 1, -4. Any questions about anything I did or why I did it? Yes. Yes. So the whole point is you can do anything where you're multiplying a row by a number, adding or subtracting the rows together, and you must include all three rows. So here, I've included row 1, I've included row 3, I've included row 2. I can use any of the rows more than once. Okay, the next step. I want this to be a 1, it is. And I'm going to use that to make this a 0, and use that to make this a 0. So the top row, I'm going to do -2 row 2 plus row 1. So -2 times row 2 would be 0 times -2 is 0. -2 times 1 is -2. -2 times 1 is -2. And -2 times -4 is +8. So now I want to add these all to row 1 to make 1, 0, -1, 5. Any questions about that? We'll keep row 2 the same. And now I want to eliminate that 4. So I'm going to do -4 row 2 plus row 3. -4 times row 2 would be 0, -4, 16. And I add all of these together to make 0, 0, -1, 3. The next goal is to make this into a 1 and use that to make these into zeros. 0 and 0. So on the top row, let's go ahead and do row 1 minus row 3. So that would be 1 minus 0, 0 minus 0, -1 minus -1, and 5 minus 3. The next step is I'd like to do row 2 plus row 3 would give me 0, 1, 0, -1. And what's my last step on the bottom row? Yeah, -R3 would give me 0, 0, 1, -3. Once I have completed Gauss-Jordan elimination, I'm done. A is equal to 2, B is equal to -1, C is equal to -3, and we can plug into our equation, which was AX plus BY plus C is equal to Z. 2x minus 1y minus 3 is equal to Z is the equation of the plane.